Sometimes on the internet, you see criticisms of people who do astrobiology or exoplanet science, like anybody who's searching for life in the universe. The criticisms will talk about how we need to open our mind and life doesn't have to look like it does on Earth. And how dare you open your mind, humble yourself. I just think it's interesting because that criticism doesn't make sense, because they can and they do and they have thought about non-carbon based life and what that would look like and how they would find it and what they've thought about that actually. It's kind of a baseless criticism, but I thought it would be fun today for us to do that. Let's humble ourselves. Let's look into it. Let's talk about silicon-based life.
Silicon-based.
Summation.
We are dealing with a silicon creature of the deep rocks, capable of moving through solid rock as easily as we move through the air.
Obviously, we have to start with carbon-based life, though. So first, carbon-based life. I'm going to choose like 3 areas to just kind of peek our heads into what carbon-based life is, because obviously this is a huge field. There's a whole huge field of research called organic chemistry. It's so important that we could do hours and hours and hours and hours, and I totally would, but not today. So we're just going to look at 3 things: chemistry, biology, and physics. Just 3 little things. Okay, the first is the chemistry of carbon. Carbon has 4 valence electrons, so it can bond to things 4 times. And I'm always so worried about doing the chemistry. Carbon can also bond to itself. It can form really strong triple bonds and double bonds and kind of build these long chains to make macromolecules. There's a database with like 10 million possible carbon compounds, and more are hypothesized to exist. So carbon's just really, really good at making covalent bonds and making little molecules, and it can act as like a scaffold, like to structure these giant macromolecules to build life. So carbon building these giant macromolecules, binding with mostly oxygen and some other stuff, builds up this huge chemical diversity that allows life to do lots of different functions. Some examples of important carbon molecules are the nitrogenous bases that form our DNA and store like information for life. It forms lipids, these fatty molecules to store energy and also like allow us to move around in our solvent. When I say us, I mean our little teeny tiny cells. It makes proteins, which do the work for our cells, and like on and on and on and on. There are so many molecules that are important to life going on in our little tiny cells, and they're all carbon. So when people say carbon-based life, this is what they mean. Carbon builds these macromolecules that are important for life to do its life business on Earth. Now move into biology. You want to take all these macromolecules and you want to like make a cell, and you want that cell to evolve. You want it to become a multicellular organism, and you want that to evolve into like a dinosaur or a rat or a flower. In order for biological life to happen, you need those macromolecules to be chemically stable for the timescale of biological interactions. So you can't stick your hand in water and have all your carbon bonds dissolve. But also these molecules have to be chemically reactive in order for something to happen. Like in order for you to break a lipid apart and get the energy out, you have to break that bond. So you have this balance beam of stability and reactivity. Your molecules have to be stable enough so your cells don't just fall apart, but it also has to be reactive enough so that chemical functions can actually happen. You have to be able to break those chemical bonds. And this has to do with the planet you live on. What is the temperature? What is the pressure? What is the reactivity of your substances? It also has to do with your solvent. In order for chemical life to operate, it needs to be inside a liquid medium that allows it to move. On Earth, our carbon-based life lives in water. The polarity of water helps in the assembly of like cell membranes and things, which means you can trap things like minerals and vitamins inside your cells for use later. And all of this leads most people to think that water might be the only solvent that is capable of hosting life. We can get into that later. I'm really speeding through this because I want to just get to silicon, but the last thing when you think about biology, it needs to operate at a temperature and pressure that allows life to thrive. So on Earth, We have a temperature that allows water to be a liquid and act as a solvent. We also have a temperature that allows our carbon macromolecules to be balanced with their reactivity and their stability. We need some reactions to happen, and we also need the lifetime of those reactions to be long enough to allow our molecules to survive and for life to thrive. It's the chemistry of carbon just being absolutely great at making these giant molecules, and then the biology of carbon allowing for this chemical stability inside of our nice happy solvent that we have on Earth means carbon-based life. On Earth, it has to be carbon-based life. And the question becomes, where does the carbon come from? So you go to physics. So Big Bang nucleosynthesis didn't make carbon, and yet, here we are, which means carbon has to be made in stars. And there are a couple of different ways. There's the CNO cycle, there is the triple alpha process, there's the PP. It all depends. Stars are so complicated. When you learn about stars, people are just like, okay, 2 hydrogens smushed together and you get it. It's so complicated. It's so complicated. And I don't want to get into it, but I do want to talk about the triple alpha process, which happens in some stars and might be where most carbon comes from. It wasn't discovered until the 50s by one Fred Hoyle. So after saying stars are very complicated and all that, I'm going to give you the kindergarten cartoon explanation of the triple alpha process. And I'm sorry about that, but you have 2 helium atoms, you have 2 alpha particles, which is the nucleus of those guys. So 2 protons, 2 neutrons, 2 protons, 2 neutrons, and the density and pressure of the inner core of the star smushes them together, and you get a beryllium. This type of beryllium is really unstable. It has a half-life of 10 to the minus 17 seconds, which is insanely short. This guy just wants to break apart. It wants to break apart into smaller nuclei. But, if a third alpha particle, so a helium nucleus, 2 protons, 2 neutrons, can slam into that beryllium before it breaks apart, you get carbon. Wonderful, beautiful, stable, life-giving carbon. And it turns out that happens a lot. Like, the lifetime of that's really short, but there's a ton of alpha particles in the core of a star floating around. Boom, carbon. Nice, happy little carbon. The first stars formed from the products of Big Bang nucleosynthesis, so they didn't have any metals in them. Well, they might have had some lithium. So in the cores of those stars is where the first, carbon, oxygen, silicon, all that stuff is made. And then they go boom, boom, and you have our process where lots of heavier elements are made. So if you want a planet around a star that has carbon on it, you cannot be a population 3 star. You can't be the oldest type of stars. You have to be in the following generations of stars. So there is this requirement, if you want life on a planet, you actually need to form a planet. So you need rocks and stuff, and you also need carbon on that planet. So the CNO cycle making carbon, the PP chain making carbon, the triple alpha process making carbon is required to get life on Earth. There is this time scale element of the universe that's like, where will life form? Well, you need carbon, and you don't get carbon until later. And that's kind of interesting. I think that's in the Drake equation. I'm not going to look it up. Deal with it. I'm about to go on a tangent about the discoverer of the triple alpha process, Fred Hoyle. Skip to this time step and I'll talk about silicon again, I swear. This will just be a brief story about the man who didn't get a Nobel Prize because he just had to be a contrarian at every opportunity. Okay, so Fred Hoyle, he discovered the triple alpha process. In one of the coolest situations I've ever heard of, the triple alpha process that he suggested required an isotope of carbon that had not yet been discovered on Earth. Yet is the word there. And people were like, how can you suggest this process when this type of carbon doesn't exist? You're saying that this makes most of the carbon, and yet we don't see that type of carbon. And he's just like, well, I'm here, aren't I? If it didn't make this type of carbon, we wouldn't be here. It has to work. And then later, they discovered that type of carbon. Neat, really cool, awesome. But here's the thing. I used to do these observing nights in Kentucky, because that's where I got my PhD. And I would give a little talk, and then we'd go to the telescope, we'd look at stuff. And a lot of time it's just people who want to learn a little bit of astronomy, and I think that's great. But because we were in Kentucky, occasionally a person, an old lady, would come up to me and she'd be like, you ever see something that's like miraculous? Like, you ever just see something that shows God, because we're in Kentucky. And I mean, that's fine. I always said no, I did not. But I did have a story about Fred Hoyle. Let me just read you the quote. Would you not say to yourself, some super calculating intellect must have designed the properties of the carbon atom. Otherwise, the chance of my finding such an atom through the blind forces of nature would be utterly minuscule. A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics, as well as with chemistry and biology, and that there is no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question. So I was happy to have this story about Fred Hoyle, and I would tell the little old ladies, and I would say, well, I don't agree with this, but here's a very famous astronomer who did find something. And I would tell them about the triple alpha process. The triple alpha process is one of those things that people point to when they're making fine-tuning arguments. The idea that you have this really short lifetime beryllium, and it just happens to have a lifetime that's about the same time as the collision frequency of the third alpha. Isn't that a fun coincidence? God is real. So the idea that we get carbon at all, you need this happy little coincidence. But on the other side of that, you have your carbon in your star. If you were to slam, another helium into it, it makes oxygen. And it's at this specific state. But if the specific state of that oxygen was a little bit higher, if it was a resonance state of oxygen, then that reaction would be favored. And instead of having a bunch of carbon in your star required to make the humans and all the things that live and breathe and eat and die, you would have a bunch of oxygen. And oxygen is not a good building block for life. So it's almost, according to astronomer Fred Hoyle, that an intelligent designer is like pushing, fine-tuning us into having a lot of carbon. And I was happy to have this story. And I was happy to tell the old ladies this story. And they would go home like, yeah, praise him. And that's fine. That's fine. But I was going to tell you this story. And I am. So I looked more into Fred Hoyle. And this motherfucker, he's an atheist. He's an atheist. He says he's an atheist. Thanks, Fred Hoyle. You ruined the little old lady's day now. What do you mean you're an atheist? Why would you say that? If you're an atheist, it's kind of mean. Now it kind of sounds like you're making fun of them, which is not nice, I guess. Did I just make fun of them? It's fine. Fred Hoyle named the Big Bang, which I also knew as a fact, but I didn't know the story behind it. Fred Hoyle was on the BBC, because he's British, giving an interview and talking about the new Big Bang Theory. Because it wasn't called the Big Bang Theory. It was some kind of new cosmology. And he said, these astronomers, they're just too religious. They just want to invoke God. They want to invoke Genesis. They want a Big Bang. And then boom, there's the universe. Because Fred Hoyle thought the universe was static. And he's making the same argument, but from two different sides for two different things. Oh, with stars, with his discovery, it's great that it reeks of intelligent design, but when the people want to talk about the Big Bang, this annoys him. How dare they have something that reeks of intelligent design? Fred Hoyle, you are a contrarian. You are just mad because you didn't come up with the Big Bang. In a quote which he says later, he almost had it. It just suits him to be religious, and then it suits him not to be religious. And this annoys me, Fred Hoyle. I do not like this. It just seems like he's being a contrarian to be a contrarian. When his idea, it's amazing and great. But when it was someone else's idea that he almost had, it's dumb and silly and wrong. And this is the worst type of person. He has this quote where he says it's better to be interesting and wrong than boring and right. And I disagree. Like, that's the whole point of the science, right, my dude? I don't understand. Fred Hoyle was a professor at Cambridge, you know, a really prestigious position. And he retired early because he got in a fight with Lyndon Bell, the Lyndon Bell, my favorite scientist of all time. I'm just not on Fred Hoyle's team today. I don't know. I've been really annoyed. Like, you can't just be a contrarian. That's not how science works, my dude. Anyway, this lost him the Nobel Prize. In 1974, the discovery of pulsars got the Nobel Prize. And this is a whole thing, but the man who got the prize, it was actually his graduate student, Jocelyn Bell Burnell, who discovered the pulsars, and they wrote the papers together, and she did not get the Nobel Prize. He got the Nobel Prize. And I've heard her speak. She's great if you ever see her. I think she's fine with it. But this is a thing that comes up where people are like, she should have gotten it. They called him for a quote at Cambridge, and he was like, well, that's weird. Jocelyn Bell discovered the pulsars. Why did he get the award? And then, because of libel laws in the UK, he had to write an apology. And in the apology, he was like, well, it's not that guy's fault. It's the committee's fault. It's the Nobel Prize Committee's fault. They don't think about things correctly. And then in 1983, when they went to give the Nobel Prize to nucleosynthesis, instead of giving it to Fred Hoyle, who, you know, did all the math and discovered it, they instead gave it to someone he collaborated with later to find that bit of carbon-12 that we had never seen on Earth before, and kind of provided evidence that his theory was correct. He lost out on the Nobel Prize because he's just constantly being a contrarian to be a contrarian, and isn't that a lesson for us all? So Fred Hoyle leaves Cambridge. He loses the Nobel Prize for being a contrarian, but we're capitalists, so he needs a job. So he starts writing sci-fi novels. Isn't this the most beautiful cover you've ever seen in your life? This book is gorgeous. Spoilers for a book that came out in 1957, but the black cloud is actually a sentient form of alien life. So suck on that, people at the start of this video who said astronomers never think about different types of aliens. I would say read it. It's good. It is a slower sci-fi novel. I would say especially read it if you are an astronomer, because I think Fred Hoyle has a problem with not only the government, but his fellow astronomers. And also, especially if you are into like the way science used to happen, there's a lot of stuff in here about photo plates and putting multiple photo plates in like a blinker so you could see any changes highlighted in the photo plates. Somebody writes a computer program and they're all marveling about how it can do 10,000 calculations an hour. Yeah, I would say read it. So we're back to carbon-based life. There was a side journey about Fred Hoyle. Who cares about that? We're back. We know the chemistry, why carbon is important. We know like biologically why carbon is important. We also know like why your planet, where your life is going to evolve is important, and why carbon plays a role in that. And I think all of those reasons together, plus like, as I said, we could go on for hours and hours about why carbon is important to carbon-based life. All of those reasons lead a lot of people like myself to the conclusion that when we find life somewhere else in the solar system or in the galaxy, we will find carbon-based life. Carl Sagan called this carbon chauvinism, and he was also a carbon chauvinist, which, great, Carl Sagan was so good at words. When you see carbon chauvinism defined, it's stated as like, because we are carbon-based organisms, our understanding of what could be outside of that arena is limited. It's harder for us to imagine non-carbon-based life. But Carl Sagan was a carbon chauvinist. So I think that the meaning has kind of been lost. I'm not a philosopher, don't come at me, but isn't this the anthropic principle? Are people against the anthropic principle? Like, carbon-based life evolved on Earth, or it was seeded on Earth. It's fine. I'm open to possibilities. And it was successful because it is carbon-based, right? Carbon-based life is the successful option, so that is the one we will find. But when I say that, and I say I'm a carbon chauvinist, that doesn't mean I'm going to turn up my nose at non-carbon based life, right? Like if one of the little Mars robots sends home a picture of something that looks like this and it's made of iron, I'm not going to be like, well, I'm not interested in non-carbon based life. I don't think that's life. I don't think that could exist. No, I'm going to be excited as heck. I'm going to raise $50 billion myself to go collect that rock from Mars and bring it back here to study. I'm a carbon chauvinist because I expect the life that we find and we will find in the solar system, in the galaxy, will be carbon-based. But I'm not a carbon chauvinist in that I will not consider other types of life we find not life. I just think it's less likely. So let's talk about silicon-based life. So I hope we have just sped through carbon because we've got carbon. We know carbon. We are carbon. And we can get to silicon. But really quickly, some definitions. Silicon is atomic number 14. It's right below carbon on the periodic table. Silicon is different from silicone, which is here. Silicon is also different from silica, which is like sand and quartz and stuff. Sand is actually really complicated. Not all sand is silica. So when we talk about silicon, we're talking about the element silicon. And when people refer to silicon-based life, I imagine, they are imagining, well, we have these giant carbon macromolecules. What if instead of the carbon, it was silicon? So you just take carbon as the scaffolding element and replace it with silicon. This is a giant 57-page review. I'm so sorry I keep suggesting 50-page papers, but it's really, really good. And it's just a compendium of 100 years of research on like silicon as an organic style of life. So again, suck it, you nerds, at the start of this video who said astronomers never think about other types of life. 100 years of research. If this is the kind of thing you're interested in and you want to follow like a scientist at the forefront of this field, the third author on that paper, Sarah Seeger, she's huge. She does chemistry, atmospheric science, exoplanet science. Like if you're interested in aliens, like look at Sarah Seeger. She's great. So let's look at the chemistry, biology, and physics of silicon. We want to make these giant macromolecules of silicon. Lucky for us, silicon also has 4 valence electrons. And I think this fact, look at the periodic table. There's carbon, carbon-based life, amazing. Look just below it. Why not silicon-based life? Is the reason we see silicon-based life so often in like sci-fi movies and things. However, as this paper states, there's surprising little symmetry beyond silicon can also form 4 bonds. So while silicon has a space available to have these 4 bonds, the bond angles in silicon are going to be different from the bond angles in carbon. And bond angles will determine the shape of your molecule. So you can't just actually take out the carbon and shove in silicon. Also, the bond length of silicon and whatever it's bonding to is going to be longer than that same bond with carbon, which weakens the structure of your macromolecule. So just taking out carbon and shoving in silicon is not going to work. You're going to have to build a different style of macromolecules. And the wrinkle here for silicon as the chemical flavor of life is the thermodynamics. It takes more energy to make a silicon bond than a comparable carbon bond. And because of thermodynamics, if something is energetically expensive, it's just not going to happen as often as something that is energetically cheaper to make. So if you are on early Earth and you are going to start making some sort of life, the carbon will always happen first. It's easier to make carbon-based life than silicon-based life. But imagine there's no carbon available, or imagine a planet is seeded first with silicon-based life and it's at an advantage because it's farther along in the evolutionary process or something. Biologically, silicon is not as good for life is carbon. When I talked about carbon, I talked about you have this balance beam of like chemical stability and chemical reactivity, and you need your molecules that build life to be stable long enough for whatever they need to do to happen, but you also need those molecules to break and do whatever they need to do. And there's a nice little happy balance with carbon. As I mentioned, silicon bonds are weaker. They're not as chemically stable as the carbon molecules. Where carbon can do double bonds and triple bonds to strengthen those macromolecules, silicon doesn't really do that. Carbon can build these really long, stable, beautiful macromolecules, but the silicon equivalent is going to be weaker. It's going to be longer because of that bond angle difference in silicon and carbon, but it can't get too long because the bonds just aren't that stable and it will break apart. So if you could actually make some life from silicon, it's probably going to be like physically a lot smaller, a lot less cells than a carbon-based life form. Another big problem though is on the other side of that coin. Like silicon just hanging out is incredibly reactive with oxygen. You actually don't find silicon just hanging out. You find silica, SiO2. And silicon is happier to bond. See how I'm giving feelings to chemicals? Silicon is happier bonding to oxygen than forming a silicon-silicon bond. It is more likely that you would have silica going around than a double bonded silicon. So where carbon will just bond to itself and hang out and build these strong, beautiful things, silicon is just seeking out oxygen to make silica. So if you did get giant macromolecules of silicon, you would have to have a whole bunch of oxygen in there. That's another problem. If you have a loose carbon floating around on the earth where you want biological life to thrive, it will find an oxygen and it'll make CO2. But that's a gas at STP. If your silicon finds an oxygen, and it will immediately, that makes sand. And we can go back to thermodynamics and say, okay, if we need some extra carbon and it's just in the atmosphere, we can break that bond. It's easy to take that carbon out. But what if we have sand and we need to take the silicon out? That's a much more energetically problematic thing to have to do. It is easy to make life from gas. It is hard to make life from rocks. Also in biology is this solvent requirement that we have, right? We need our cells to be able to move around. We need to have like cell walls that can open and push things out. We need the solvent, we need water. And silicon molecules just dissolve in water. They just break apart. If you built in a lab a shelf-stable silicon cell and you plooped it down in some water, it would just dissolve. And that's not really great for evolution if the building blocks of your life just dissolve in water, right? So on Earth, silicon life does not work because we have oxygen in the atmosphere, which would take all the spare silicon and turn it into sand. And if we were able to build some molecules out of the silicon, it would just dissolve in water. But you know, what if you didn't use water? Like, let's open our minds. Let's open our minds and humble ourselves. Maybe you have a planet that's not water. It's got sulfuric acid or something where silicon molecules of all different types do not dissolve. Maybe you could get silicon-based life there in your sulfuric acid. Maybe. So now we're kind of limiting ourselves to planets where there's not enough carbon to make carbon-based life, which is a big jump. And also the solvent on that planet is going to be liquid sulfuric acid. So sulfuric acid is similar, like temperature-wise, to water. So like if you had sulfuric acid in your hand in a jar with a glove that you're wearing, it would be liquid at room temperature, okay? Which means the reaction rate, which depends on temperature for a sulfuric acid, should be about the same for our silicon-based molecules as it is with water, which means that, again, silicon-based life is just too reactive. Even if you have a nice solvent that works well with your silicon molecules, it doesn't overcome the bond angle problem. It doesn't overcome the bond strength problem or the bond length problem. The structure of those molecules is just not good enough to build a giant organism, even if you're in a vat of sulfuric acid. And so the next thing you could think is like, okay, well, what if we lower the temperature, right? If you lower the temperature of the planet you're on, the reaction rate goes down, just broadly. Come at me, chemists. Broadly, temperature goes down, reaction rate goes down, right? So if you have something super reactive, like all your silicon organisms, you lower the temperature, the reaction rate goes down, it's a little bit stabler, right? Maybe you could finagle the temperature of your planet so that this little balance beam of reactivity and stability is balanced for silicon. And it's like, fine, but you need your molecules to be at least a little bit soluble in your solvent, you know? And the lower your temperature, the harder that is to do. So even if you lower the temperature to lower the reaction rate, now you've lowered the solubility, you've just increased the barrier to making giant silicon organisms. Y'all, it's just not gonna work. You have this chemical problem, you have a biological problem, and now let's do the physics. So silicon is also made in stars, and also as a result of like the supernova process, there is way less silicon than carbon in the universe. So carbon is just more abundant. But you have this similar situation. If you're going to build your silicon-based life, you need it to be in a second generation star, at least where you have enough metals to make a rocky planet, mostly out of silicon, right? Because silicon is rocks. And I think this is the biggest barrier for silicon-based life. If you have a planet that has silicon on it, it's also going to have a bunch of carbon on it. And if life is going to spring up on this planet, it's just a lot easier to be from carbon. So wouldn't it be from carbon? Wouldn't it? The silicon is going to be stored in rocks and sand and quartz, and the carbon is going to be in the earth, it's going to be in the air. It's just so much easier to grab some carbon and make some macromolecules than break down a rock and take some silica, because it's not going to be pure silicone, because it's going to find some oxygen to grab onto, and turn that into life. It has to be carbon, because carbon is easier. It's easier to make life from carbon than it is from silicon. Imagine you have your very first RNA molecule and your very first silicon equivalent of RNA on your new baby planet, and the atmosphere is all orange and there's no oxygen in the atmosphere yet. These guys are on a race to be the dominant type of life on your planet. Your silicon is going to be much weaker. The bonds are easier to break. It's harder to make big molecules. There's not a lot of silicon available. This guy is going to expend all the energy it gets trying to break the sand down to build more molecules, right? Whereas this guy, he's carbon-based. He's got it free and easy. There's carbon flipping everywhere. Which one of these is going to win the race? Because as soon as one of these starts respirating and putting oxygen into the atmosphere, all of this is off the table. Once there's oxygen in the atmosphere, any new type of life that tries to form is just going to be broken apart, because oxygen's crazy reactive, right? So in this race, carbon's always going to win. Carbon is always going to be the dominant type of life that comes out. This is just not an option. It's hard to turn sand into life, right? That's why the aliens won't be silicon. I should end by giving you a top 3 list, so that later when you're having an argument at a bar, you can remember the list without pulling out your phone and ruining the conversation. The top 3 reasons the aliens won't be silicon. First, the macromolecules that could maybe be produced by silicon are not going to be nearly as strong and good for life as carbon. Because of the bond angles, you're going to have these different weird shapes. Because the length of the bond is just going to be weaker. Silicon can't do double bonds or triple bonds. The overall macromolecule will be weaker, which means life is going to be harder to make. The second reason is that silicon molecules will just dissolve in water. Water is expected to be the universal solvent, and if it doesn't work in water, it's not going to work for life. And number 3, the most important reason, why would it ever be silicon when carbon's like right there? In the race for life, carbon versus silicon, carbon is always going to be more efficient because of all those thermodynamics reasons, and because it's much harder to turn sand into life than it is to turn a gas into life. If carbon's right there, it will never ever be silicon. The aliens won't be silicon. This is unrelated to silicon aliens, but the idea of life evolving on Earth is like you have the building blocks of life and then some sort of catalyst, like lightning strikes or something. And you might have seen this experiment where they simulate that and they produce like amino acids and stuff. Or you could have those things on comets that slam into Earth because the solar system was a lot more violent when like life started evolving on Earth. It doesn't matter where it comes from, but you have those tiny, teeny building blocks of life, and they have not yet assembled into being life. And then the most bonkers, new, crazy idea, the clay hypothesis. It's the wildest thing I've ever heard. You have RNA, but it's not self-replicating. It doesn't have that ability yet. But before you can evolve life, you have to replicate. You have to build the same thing over again with some genetic diversity. The clay hypothesis suggests that RNA, before it can self-replicate, used clay as like a catalyst for reproduction. So the RNA would just lay in this soft, smooth clay and get off of it. And now there's like a little pattern that all the other little molecules would like fall into and make a new RNA. And that's how you could replicate before you get ribosomes that can do the catalyst for RNA replication on itself. Isn't that the dumbest idea you've ever heard? Oh, we just make a little pattern in the clay. I learned about it in this book. You know, this is like an astrobiology class you would take. And they've done experiments and like provided evidence for this idea. You take the clay and it turns into like a teeny tiny pre-cell. It's not organic, it's biologically inert. And the RNA can use this little clay cell as a tool to replicate before it could replicate by itself organically. That's so cool. It's the coolest thing I've ever heard. And every time I relearn this fact, I'm amazed that it happened and that it exists. Like, it's such a bonkers idea to even come up with. And then to be like, oh, we could just test it. And they tested all kinds of different ways. And the little building blocks of life can use clay to make life. That's so cool. By the way, clay is made of silicon. So the silicon's important to life on Earth. It's just, it doesn't make organic material, but that's pretty cool.